Hello, everybody. Welcome back to our very first Future in Space Hangout for 2018. My name is Tony Darnell. I work at deepastronomy.space, and today we are going to dive in to and revisit the Transiting Exoplanet Survey Satellite mission and give you guys an update on where it's going and when it will be launched and what the schedule is and all of that kind of stuff. And to do that, we've got two guests from one of which you've heard before, Dr. Sara Seager, and also we have Natalia Guerrero with us as well to give us an update on what's going on with TESS. And I know most of you have been asking about what's going on, so this is your chance to find out. We are streaming live on YouTube, Periscope, Facebook, and Twitch. So there's plenty of places for you to interact, but I'm going to ask you to please, if you could, use our Discord server, which is the link to that is in the description of these videos. I am looking at it right here on my tablet, and I'm seeing already people showing up. One Plot's here, Larry Keys, Uncle Bill, all the regulars are here. The reason for this, folks, I know you'd rather use the chats on all the platforms. I get that. But for me, I can't monitor all four of them at once, and I miss things. And besides, when the live stream is over, the chat disappears. Here, at least, we capture all that stuff. So if you can stick with it and use the Discord chat, that would be awesome. Okay, so Harley's not here today, so he usually introduces our Hangouts. But I want to tell you that these Hangouts are sponsored and endorsed by the American Astronautical Society and the American Astronomical Society. And they are designed to bring the latest in the Future in Space Hangout that we're in now is designed to give the latest in both space astronomy and human spaceflight efforts that are happening around around the globe, and with an eye toward what's happening in the future. So that's what these Hangouts are all about. I want to thank the American Astronautical Society who sponsor this particular Hangout for their membership, and we'll just go ahead and get started. So let me bring up my panel. Hi guys. So joining me today, Alberto's here. He's in the lower left or the lower right, sorry, and he's gotten back from jetting the world and telling everybody about JWST, and he's here in our Hangout today. Welcome, Alberto. It's good to see you.
It's good to see you too, Tony. Thanks for having me.
And I just need to apologize in advance. I've got bronchitis, and it's not going away. So I'm trying to get my cough under control here while we do it.
Drink more.
I've got this giant glass of iced tea here to keep me hydrated. Okay, and so joining me as a face also from these are from the Massachusetts Institute of Technology. My two guests, Dr. Sara Seager is in the lower left panel there. Hi, Sarah. It's good to see you back again.
Thanks for having me back.
Good, and you're always welcome here. And in the upper right is Natalia Guerrero. She is a are you a postdoc, a grad student? What's your?
So I'm a research associate at the Kavli Institute at MIT, and I work on various parts of the management for the data pipeline and other parts of the TESS data.
Oh, really? That's cool. I worked on the data pipeline for the Dark Energy Survey, so I know a little bit about what you're doing. So that's awesome. I have some questions for you a little bit later on. Also, in the upper left is my good friend Carl Clark. He is helping me on social media. He'll be answering questions, looking at things, getting me posted on some of the comments and questions that you may have, which I hope you have bunches of as we go along. So here we go. Okay. The TESS mission is designed to look for planets around other stars using the transit method. That's what the T is for. And you guys have heard about that before. It's where the tiny dips in brightness of stars occur when planets move between us and the star's light. And TESS is an instrument that is unlike any that come before it. And so, Natalia, I wonder if you could just give us a brief summary of what the TESS mission is designed to do, and then we'll talk a little bit about some of the schedule that's coming up with the mission itself.
Sure. So TESS is an almost all-sky survey, and so it's different in that it can see a large swath of the sky at a time, and so it's going to look at the sky in these long vertical strips called sectors, and it's going to stare at these sectors for orbits of 27 days And we're going to take data every 2 minutes for stars that we've picked out already in a candidate target list. And so we're going to take images every 2 minutes of those stars. But every 30 minutes, we're going to have an image made of the whole field that we're seeing. And the cameras have like a really wide field of view. So you can fit Orion into one camera. So if you've seen Orion on the sky, it's pretty big. So this is a...
Let me pull up this image that we have from the right. I'm sure I'm sharing it now.
Yeah, exactly. So the cameras have a very wide field of view, and this is really useful for just grabbing and having a really high frequency of taking images, so we can really see when these transits happen and have a very fine-grained cadence of these images. So it's, as you said before, we're looking for transits. So we're looking for, in these images, the light from a star decreasing with time and then increasing again. And we think that that's, and what we're looking for is signals from a planet passing in front of a star. So this is what you said before, the T in transit. So that's what TESS is going to do. It's going to be a nominally 2-year mission. And first it's going to look at the southern hemisphere and then the northern hemisphere and hopefully find thousands of exoplanets.
Now, we've talked to almost everybody that I think is watching this has heard about Kepler, the Kepler Space Telescope, and it looked at one area of the sky in the constellation of Cygnus for, I think, 5 years, and it was designed to find Earth-like planets around that around stars in that patch of sky, and then, of course, it's been spectacularly successful in finding all kinds of planetary candidates. How does TESS compare with Kepler?
Do we have, Natalia, do you remember if we have the video on the TESS website, the one that shows like zooming away from Earth?
That is a good question.
Is it?
I can pull it up. I think I know what you're talking about.
Is it this one, Sarah?
I don't, let's see.
It says.
Yes.
Yeah,
this
that's
one?
the one.
That actually, we do have a video. It was made by Zach Berta Thompson. He's now a professor at the University of Colorado. But the reason is, in astronomy, we want to look at the very nearest objects. Photons are like the brightness of the star. That's our currency. So the more, the better, actually. And you can see here, zooming away. I can't actually see that on the screen, though. But you can see the TESS predicted the anticipated planets and how they're all very much closer to our own Earth, which is at the center of this animation. The Kepler stars it's actually a completely different mission, but by design, they're actually quite far away, thousands of light years compared to hundreds of light years. And it just makes the stars way brighter so we can do a whole host of follow-up measurements. And that's the point of the TESS mission, to look at closer, brighter stars than we did before.
Okay, I'm trying. Yeah, so the color coding in this. Is this the reason you can't see it because I don't have it centered, Sarah?
No, I just didn't see it zoomed in my. There it is. Okay.
Okay. So I'm seeing the color coding here, and the yellow is what TESS is predicted to find, and the blue, which there's a few blue stars.
Right, blue is Kepler.
Yeah.
So in these circles are
there's one. There's.
Yeah, if you zoom out, you'll see it. TESS TESS is designed to search the nearest stars. Oh, and there's the Kepler field of view, and that's why they're all bunched into one area, because it only looked at one area of the sky during its mission. But TESS is designed to look around the entire sky. And what was the cadence again, Natalia? What did you say? Every how many minutes? 2?
So we take images of like a specific list of stars every 2 minutes. So we cut out little pieces of the field of view and download those every 2 minutes. But we stack images of the whole field of view every 30 minutes.
And those do get downloaded, correct? Those whole field, the ones that would cover the entire constellation of Orion, those do get downloaded and then stacked on top of each other?
The stacking happens on the spacecraft. So
you do it on the, okay.
Yeah. Movies or soccer game or whatever. But the spacecraft really have a very later rate, so we can't actually send out the information now. We have to do some board the spacecraft.
So yeah, so can you give me a sense of the technology? How big would one image be if you just download every single frame?
So the
how much do you think your phone camera is these days? I think to each test camera, I want to say it's about 16 megabytes for the one camera, or one CCD rather.
Right. So but my point is that you're getting a lot to download each individual frame would be a lot of throughput on the system on the Internet of Space, which I guess is using the TDR system.
As Sarah said, that you might not be interested in, right? So you just want to maximize the throughput for only the data you're interested in.
Right.
Well, the funny thing is that about that is one person's junk is another person's.
I know.
So sometimes on the mission, we're like, you know what? The best science that comes out of it it's hard for me to say this as an exoplanet person, maybe something other than planets, because there'll be so much data that everybody can use. So I just looked it up. Each camera has 24 by 24 field of view, and it's basically about 16 like I said, about 16
megabytes per frame.
Per frame.
Mm-hmm.
Wow. So okay. So one plot is commenting on Discord. Didn't Kepler have an 80-day period view? That's K2. K2 was the rebooted Kepler. If you'll remember, two of its reaction wheels died on the original spacecraft, and what they did was absolutely amazing in terms of ingenuity, in my opinion. They decided to use the pressure of the sun, the radiation pressure of the sun, as one of the ways in which they could stabilize the pointing of the Kepler spacecraft. So now it sweeps along the ecliptic plane. That's the path that the Earth goes around the sun, and that as the Earth and Kepler go around the sun, there's an 80-day period of each field of view, and then it has to switch to another field of view. But Kepler, when it was originally designed, only stared at Cygnus, the constellation Cygnus. So that's the difference there, one plot. So okay, well, what's the latest, guys? I mean, so the Kepler, or the TESS mission got delayed. I believe it was supposed to launch last year, August of last year. It got delayed. What's going on now with the mission?
Natalia,
you want to let us know? I should say, Natalia. What's going on?
Tell us about it. There you go.
Sure. So the launch has been pushed, but we actually just got word that TESS's cameras were tested, and the performance was measured at MIT, and then those were shipped along with other parts of the spacecraft to orbital ATK in craft, and it was shipped to Kennedy Space Center last week, and it arrived there this week. And so there will be social media postings about its arrival probably this afternoon. So that is where TESS is right now. That is
great news. Yeah, we just received, just right before this hangout, we received that the news announcement went out that TESS has safely arrived at Cape Cod. So it's like Cape Cod,
on vacation.
Cape Canaveral, and it's all safely there. So it's kind of out of our hands now. And I hope you too appreciate this is such great news for us.
It's fantastic.
Yeah, that is great news. And it is going to be launched, am I right, on a Falcon 9?
Yes.
Yep.
And so while it's at Kennedy, now that it's there, now that it's been tested, you guys have signed off on the detectors, which if I'm remembering my news right, that's sort of what the delay was about. There was some issue with the detector's noise, or maybe there was some quality with the detectors or something like that had to be looked into a little bit closer. Am I right?
There was an issue with the focus, but we didn't delay for that for any reason. The delay in general is just general things. Like anything you build, it always takes longer than you expect.
Yeah. Right.
There was sort of a series of those kind of general delays. There wasn't anything like crisis or serious that caused a delay. There were some issues, but they're livable with.
Okay. And so while it's at Kennedy, now that it's there, I guess the next step is to get it packed up and put on a Falcon 9, right?
Mm-hmm. Mm-hmm.
Yep.
Any idea when we might? Is there any schedule for the launch yet, or is it too soon to put a date on that?
I think it's the nominal date.
Yeah.
Oh,
well,
yeah.
If you read the press release, and we do go by what NASA says, they say spring 2018.
Spring 2000. So there you go. It could be anywhere from March 21st to June to the summer.
That's probably a good way to
Yeah.
go.
The NASA website says April 16. So
Okay, there you go.
So is it? You said it's out of your hands now that it's at Kennedy. And I suppose they have. There's probably some, and maybe Alberto, you can comment on this because you're familiar with how JWST is going to work. They give the spacecraft to SpaceX, who I guess signs for it, and then they take it from there and put it up on the rocket and get it ready to go, something like that. Maybe.
Yeah, to do that, it's a little more complicated than that. It takes a little, to make sure that everything works. I don't know exactly how it works with TESS. Like for JWST, for example, it has to be powered to make sure that everything is clean. I'm sure it's not that different than what it is for TESS. I don't know exactly what the procedures are, but it's a smallest payload, but it's still, nevertheless, they are very complex and sensitive cameras. You just want to make sure they work, right?
Okay.
You don't contaminate them, right?
All right, well, Achilles 308's asking, does TESS have any folding components or anything that makes you nervous about deployment?
Believe it or not, like in order to get NASA to select TESS, we try to answer,
right.
Those questions are asked all along the way. So the only foldable item actually is the solar panels. They're folded up and deploy. And that's the only deployable. So no, not nervous.
And that's
almost just like JWST.
Yeah. Yeah. It's not origami. I guess I don't know about you, Alberto, but I think everybody is like, really like, oh my God, that's going to be a tense period of time.
But it's good. I mean, no, but I think Sarah makes a good point. I think simplicity, helps in this case. You have just, if you look at the spacecraft, it's it's much smaller than JWST, but it's also simpler in a way. And
well,
so,
isn't this a special class of NASA satellite? Is it an Explorer class, or they have different? NASA has different classes of missions, right?
Right. And each class is a certain cost cap, which
Right.
kind of implies a certain risk level.
Yep.
And so TESS, even though it's super expensive, but space costs 100 times more than anything on the ground. Even though it's expensive, it's in a lower class, way lower compared to James Webb.
Well, Kepler was designed to look for Earth-sized planets around other stars, and because of that, it had extremely sensitive detectors. And by sensitive, I mean it could measure very, very tiny variations in brightness. And and so presumably TESS is on order of that sensitive, correct?
Not quite, actually. Not quite.
Oh, because the trade-off is the wide field of view, right?
Right.
So if you've got a really big field of view, you get more stars at once at the expense of maybe some sensitivity, right?
Right.
Okay.
Yeah.
Okay. George Caldwell is asking, will TESS be at L2?
No, actually. So TESS is in a really unique orbit. I think there's an animation of this as well, Carl, if you want to find that on the TESS website. TESS is going to be in a new orbit that was specifically designed for this mission. It's a 2-1 resonance with the moon, and it's a really stable orbit, which is very exciting. So it means that the spacecraft uses very little propellant each time it needs to readjust and move to a new sector. I think it's something crazy like 10 grams of fuel.
Now when you say it's a 2-to-1 resonance with the moon, that's so TESS is going to orbit the Earth twice as fast as the moon does, or twice as many times as the moon does. For every 2 orbits of TESS, there will be 1 orbit of the moon, or is it the other way around?
Oh, here we have the animation is up.
It's just an image, not an animation.
Oh, okay.
But I'll keep looking. But I figured this was better sooner than later.
Yeah.
Okay. And so what do we have here? We have the red line is TESS. The green is, what's the green?
So that is the sort of the wind-up orbit, I'd call it, is how we're going to use like the gravity from the moon to slingshot into this bigger red-shaped orbit, red-colored orbit.
So the moon is coming around in this big gray circle, and then the green orbit you're going to use the moon to help it insert itself in this red orbit here.
Right.
Okay. And this will allow TESS to see the entire sky?
What do you mean by that?
Well, I mean, isn't TESS planning on imaging the entire sky?
Right.
Yes.
The orbit isn't really related to that. It's just, Earth is really bad for astronomy. Even above Earth, if we're orbiting Earth, it's hot, it's bright. And so the goal of TESS, you can see from this orbit, is to be far from Earth. And because of Kepler's law, TESS will move much more slowly when it's far from Earth. And when it's closer to Earth, on the bottom left of the diagram, it'll zip by. So this orbit actually just enables TESS to be in like a dark environment without the bright clutter near it. And that's kind of why it's in that special orbit. To go to L2 would be better, but costs way more. And then your spacecraft just has to be more capable to transmit, data from that far away and everything. So that's what the orbit's for.
Okay, I want to put this up just so people can see. This is the sky coverage map of TESS. It's in the globe here. These are I guess this gray area is going to be blind spots around the area where TESS will not see. But every 27 days it'll be seeing this blue area. Every 56, 54 days it'll be seeing the brown area, and on and on. So we're going to get quite a few images of the celestial sphere when TESS is up. What's the mission length of TESS? How long is it supposed to be running?
Nominally 2 years. So 1 year to image these long vertical strips that map out the southern hemisphere, and then the second year will be mapping out the northern hemisphere.
Okay, and Natalia, you said at the beginning that you already have some candidate target stars that you guys are going to start with. Where did those come from?
So there's a bunch of different lists that go into making our big catalog. So so first there's this thing that's like the TESS input catalog. And so that's this giant catalog of basically every star in the sky. And from there, winnowed it down to a shorter list of stars that are like the brightest stars in the sky. Because as Sarah said, we want to be able to follow up from the ground of things that are bright, even on the ground. This is stars that we think are strong candidates for exoplanets, and Sarah can say more about that. And then stars that are proposed for astroseismology, so better understanding the behavior of stars, and then stars that are proposed by the Goddard Guest Investigator Program. So those are all compiled into this catalog.
Okay, and so it looks like Carl's got the animation going.
Yeah, the orbit.
Of the orbit. So there's...
Here, I'll rewind it real quick. So
yeah, so we can take a look.
There we go.
So we can see the moon going around, and then TESS's orbit. That is a strange orbit.
It goes twice as fast as the moon, right?
Yeah.
Around the Earth. But it's also, I think it's also higher at all times. It's higher than geostationary satellites, right?
Right. It's
so I think the closest approach is when you dump the data.
Yeah, that's right.
Yeah.
Okay.
It's actually an interesting orbit that for other things Northrop was looking at for smaller satellites. A very, very interesting orbit, actually. You can get a lot of stuff done. So
pretty interesting. It's the first time it's ever been used.
Yeah, correct.
It's quite popular for astronomy and other things.
Yeah, I agree.
What is it again?
And
what are you talking about?
The orbit. It's very unusual.
It's never been used before.
Never been used. Yeah.
And one of the perks of it, if I'm not mistaken, is the Earth and the Moon don't block the field of view very often at all, if ever. Correct?
I think so. I would have to look at it. Yeah.
Yeah. Okay.
Well, occasionally, but yeah, not too often.
Yeah. Actually, the other important thing is, Tony, when you look at the coverage, is there was a little circle in the coverage image that you showed that is the JWST continuous viewing zone, right? Where TESS will reach hundreds of days of observations, which makes it very interesting. Actually.
Oh, right. There's a little dotted line here that right up here at the top. That's, well, let me get on the...
yeah, no, I can see it, yeah.
Yeah,
so,
this right here is where JWST will be looking.
That's the JWST continuous viewing zone, yeah. So where JWST can look at any time, basically. And so you can see that there's a lot of observations by TESS there, which is, I'm assuming by design, Sarah or Natalia. Right? Yeah.
I got a good animation of it here. I'll share the screen again.
So no matter where JWST is in its orbit, it'll always be able to look there.
Yeah.
Okay. All right, go ahead, Carl. Let me pull this up.
Yeah, this is I love this animation. Actually, that's great and shows how TESS actually, takes the data. So.
Okay, we'll take a quick look here. And while this is going, one plot is asking, will TESS data be made available to the public like Kepler's, and will the format be the same? Natalia, you're working on the data management.
Yeah.
You going to make it available right away, or are you going to hang on to it?
Yeah, so one of the exciting things about TESS is that it really is very different in that there's no proprietary period on the data. And once it passes through the data pipeline, it is pushed to the Mikulski Archive for Space Telescopes, or MAST, as most people know it. And
that's where Hubble data goes to, by the way, folks.
Yeah. And the pipeline is very similar to that was used for Kepler. I think the thing that'll be different is the layout of the cameras is different. Mm-hmm. And so stay tuned for release notes as those start populating.
So Alberto, even you can download the data and use it for stuff.
There you go. Everybody. No, but it's great. So actually, is it true also that, like it was for Kepler, that as you get more and more observations, you actually get better and better at nailing down on planets, I suppose? I mean, like longer period planets, for example.
That unlike Kepler, which looked at the same field of view for 4 years.
Oh, true. Sorry.
We were just switching fields.
Yeah.
But where the overlap is at the ecliptic poles, we'll get better and better data for transits as we accrue transits.
I see. So the function is different. I see. That's right. Okay.
So what wavelength are we dealing with here? I don't recall what Kepler was. I think they were just visible light detectors, weren't they? Is that the same as TESS?
Mm-hmm. Yeah. Okay. The TESS is in the visible band. So starting at the greenish bluish range and like going all the way into the red. And there's like a hard cutoff on the shorter wavelengths, but there really does allow for a lot of light at the redder wavelengths. And this allows us to image stars that are brighter in the red wavelengths. And so one of the types of stars that people are interested in looking at are M dwarfs, for example, which are very red.
Okay, now Larry Keith is asking a question tailor-made for you, Natalia, and and I can say that Larry is very interested in data processing and doing it himself. He even does it himself. Would someone discuss the processes done on the spacecraft and with the mission data and how it is downloaded or downlinked with the bulk data transfers? He wants to know how much data processing is done on the mission data.
So on the spacecraft, what we talked about before is the images are stacked. So we get these 2-minute images and then these 30-minute images. And the 2-minute images are what we call postage stamps. So what I was saying before, these cutouts of specific stars that we are interested in, that we want to look at every 2 minutes. And so all of the data is downlinked through the Deep Space Network and then comes to MIT to the Payload Operations Center here at MIT. And then from there, it's passed to NASA Ames, and NASA Ames runs their data pipeline, which if Larry is familiar with how Kepler reduces their data, they have all of their, we use a lot of the same terminology as they did of objects of interest and the same sort of software products.
Okay, well that's a good point. So I want to bring up, you brought up Kepler objects of interest, or KOIs. There's going to be presumably a TOI, right? A TESS object of interest that it's created.
Before we get to that, I just wanted to offer him a little more detail if he wanted.
Yep, go right ahead, Sarah.
So the spacecraft has its own stuff, and it sends down in kind of funky compressed, bits. And that gets all packaged into a FITS file, which all astronomers use. It's just a certain data format. And there's several versions. As Natalia was saying, we have one for 2-minute cadence. We have one for full frame images. And those products are initially calibrated. So for example, if there were, thinking of other missions, I don't know exactly how TESS will look, but just weird column, if the columns are rows or certain things that the mission understands about the hardware that is responsible for, that will get calibrated, that will get fixed. So there's what we call the calibrated full frame images and 2-minute cadence, these FITS files that you'll get. But just like the Kepler products that Natalia was referring to, there's actually other, even more processed data that will be made for you, because NASA wants everyone who wants it to be able to use the data. Mm-hmm. So then you get what we call detrended data, where trends like from temperature or drift or any number of things are actually removed from the data. It's all really nicely cleaned up. And then in addition to that, what Natalia can talk a bit more about is even more data products like what looks like transits will even be told to you, and you'll get some nice data products that help you sort through that yourself. So there's almost any level. You won't get the pure raw data. That is not going to be given to you. Just slightly treated to full, wow, here's the list of transit-like objects. You'll get everything.
Will you get light curves?
You'll get light curves for the objects that trigger, that they have enough signal to look like a transit.
Okay. Wow. That's...
Yeah.
Yeah, and Larry, I just point out, if you've watched our Telescope Talk Hangout, you know about things like bias and flat fielding and dark field corrections. All of that stuff it needs to be done first before all this other stuff that Sarah was talking about. So raw data, not as useful because it's full of all that stuff, and you got to get rid of it first. But I just want to clarify this detrending thing. There are areas in the data, and time series data, that have trends in them that are removed. Is that what you were? Can you help me visualize what you mean by detrended data?
Yeah, like when you think of a star on a graph, if you measure its brightness as a function of time, you expect it to be fully constant as long as the star doesn't have spots or other variability. But in fact, it's not. Your measurement of brightness of the star as a function of time, it could be kind of drifting upwards like that. And that may be because the star's position is drifting within a pixel or over some pixels. It could be like on Kepler, for example, if it's the batteries are getting warm and cold as they're cycling, or other issues like that.
And that's all been removed.
Yeah, that's been removed.
Okay.
Sometimes we don't even know the physical cause. There's just stuff going on. It's a kind of black art, unfortunately, sometimes.
It is. It really is. Yeah.
All the reasons why the stars are behaving the way they are, and then remove it according to a prescription formula. But yeah, astronomers have a kind of, I don't know, I could say bad habit of just moving trends in the data.
Okay. All right. Well, that helps. So Alexander Reinders is afraid of all kinds of things. Let me get it off his chest. First of all, he's worried about the orbit. Is TESS going to like crash into space junk? Is there any danger of that? Is there like, based on that orbit, is it going to fly through a bunch of stuff?
Well, in its orbit, there's nothing else sharing its orbit, so it shouldn't have a problem.
Right.
But he's right to be scared, because frequently for everything, there's a chance of collision. In fact, I have a CubeSat that's in space right now. It's called Asteria. It's actually operated and was built by JPL. And we deployed from the space station. And I want to say a week or two after we deployed, we got a warning from JSPOC saying, you're going to come within 400 meters. That sounds far, but it's like right adjacent, 400 meters to another thing. And that was one that had deployed in the same sequence as us, actually. So stuff happens, but I'm not too worried about it right now.
Well, there's also a Tesla out there now, too, so you got to watch out for cars. Now, traffic is an issue. Okay.
They're giving you warnings. Everything is tracked. You can be let known. And if you have propulsion, you can try to get out of the way. So I think for TESS, if it's let known in advance that it's going to collide with something, it has propulsion on it, and it could hopefully move out of the way on time. So I would lay that worry to rest for now. Okay.
Well, he also wants to know about the chips on. This is Alexander Reinders again. By the way, he attends my Telescope Talk Hangout. He's an expert amateur astronomer imager. He's got some amazing imaging equipment at home. And he wants to know if the chips on TESS are CMOS or not.
They're CCDs, actually.
They're CCDs. And what is the advantage of one over the other? CMOS is a newer technology, but my understanding is they have faster frame rates, meaning you can read them out faster, but they have higher noise. And CCDs are able to have less noise, but they read out slower?
Yeah, those things are true. I think CMOS is very new for astronomy right now, so I don't think people have fully... obviously we're not talking about my CubeSat, but we use a CMOS for that reason. We need to read out very quickly. But traditionally in astronomy, to my knowledge, someone else can add on to that, the CCDs just perform the best in terms of sensitivity. And the other thing I don't think CMOS have reached yet is just the dynamic range is better for CCDs, as far as I know. So
now, dynamic range is how wide of a data path you can have with the data. Like a pixel can be from 0
star, and they can still work well together. You can have a bright stars and fainter stars on the same detector, and you're just as sensitive to each type.
Right. Okay.
I don't think CMOS has been used much, and it's not quite as far along, not nearly as far along as just this so-called deep well depth and the very sensitivity. But it's a good question. We'll see where astronomy takes it.
I know it will be interesting to see. Now, right now on your cell phone, those cameras are primarily CMOS detectors in there.
Right.
So, but like as Sarah says, it takes a while. I mean, TESS. When was TESS first conceived, Sarah? How old is the idea of TESS?
It's at least 10 years old, and actually, I don't think CMOS are really on our radar back then.
Yeah,
so
that's the point I was getting at. So back then, when these space instruments have to be built and designed, things happen in the interim that come along that are great. But
by lifting it up with a Saturn V. So
I don't know, but I mean, it's hard. All large missions take time, and I think it has. I didn't realize it was 10 years, but I guess you mean from conception to launch, let's say, Sarah. Yeah. So I guess for an explorer, that's maybe that's typical. Actually, I don't know. I haven't looked at that. So for flagships like JWST and Hubble, it takes decades, right? Maybe 2 decades, right? 17 years plus or something.
Oh, okay.
So
well, am I back? Can you hear me?
Oh,
yes, you're back.
Yes,
you're back.
Yeah. So sorry about that. Still have ISP issues. Thankfully, it's better for now. Well, Alexander Rangers commented while you guys were talking that Sony closed its CCD production in March 2017, which is why he was asking. So, but these cameras are built from the ground up by specific, by the missions themselves. They don't rely on, say, at least I don't think they do, rely on like Sony or places like that to get their stuff.
Even a mission like an Explorer class doesn't rely on commercial products. In fact, Lincoln Lab, MIT's Lincoln Lab, fabricated the CCDs. It's all in-house.
Correct. These are
yeah
very special CCDs, right? So,
yeah. So Larry Keese is commenting, thanks, Sarah. That was great. He's happy to hear that the postage stamps. Oh, he's asking, can the postage stamps be changed? I hope. I don't think they can, right? I mean, these are all images where you're looking at a certain star.
Change how?
Yeah, I'm like, you want to clarify that, Larry? I'm not sure what you mean. So it's also, Cosmic Lettuce is commenting, it's also useful to have the raw data along with the calibrated data so others can create their own calibrated data. Well, no, because actually there's only some calibration images you can only take from the spacecraft itself. For example, a bias has to be taken from that camera at a time near the exposure of that image. You can't just make your own bias. Same is true with dark current. You can't make your own dark image because it captures the characteristics of that camera at that time. You can't just make your own dark. So some you can't really make your own calibration images.
But as far as the postage stamps are concerned, it is all in software. Like you tell with spacecraft which parts of the detector you want to have the 2-minute cadence and downlink. I doubt we'll change them, once TESS is in orbit. But segment by segment, there's a whole procedure that is set up to merge a bunch of requests that are all formally defined in advance. So they are chosen they are being chosen in advance. But if something emergency or super exciting came up, it can
I'm not sure what that was, but I'm glad.
Well, that was an echo. Yeah.
Yeah. Okay. So let's see. What Alexander Race? Let's see. Hang on. Alexander Rangers also wants to know what the focal length is on TESS. The focal length of the telescopes. Now it has. Can you describe that a little bit for us, Natalia? It's got 4 telescopes, right?
Yeah. The telescopes are different, I guess, from what you'd think when you think like JWST or Hubble, where we don't have mirrors. It's 7 lenses, and the focal length is actually very short. So that we get, they're kind of like fisheye lenses, so that we can get this whole field of view onto the detector. And these CCD and the detectors are pretty large, and so the focal length is pretty short. It's, I think, on the order of millimeters. I'd have to check. There might be a cutaway on the website of what the innards of the camera looks like. And we want to be able to get, because we span such a wide range of wavelengths, we want to be able to get most of the wavelengths into a soft focus.
Now, excuse me, I was reading the writer's guide earlier today, and you guys have some expectations on how many exoplanets you anticipate finding with TESS. You want to talk a little bit about that and how you arrived at those expectations?
I'll let Sarah take this one.
Okay. Well, so basically a student here under the supervision of another professor, they spent like 2 years simulating the anticipated number of planets. And the way they did that was thinking about all the noise sources on TESS and what we call the sensitivity. So how precisely can it measure light curves for transits? And then thinking about what we know or can guess about planet populations. And that's where those numbers came from. And it's on the order of thousands of planets. So TESS is expected to find thousands of planets. We're not really any more specific than that. You can go to the website again and look for there's a bar chart somewhere that shows kind of the anticipated expectation.
Yep.
Okay. And related question, one plot is going, okay, so you expect to find thousands of planets, but any expectations of discovering habitable planets? Your secret expectations,
Absolutely.
Not your public one, he's saying.
I would say that that's a great question, and certainly a bit tricky, because we never want to be misleading, or we don't want to mismanage expectations. But certainly the world, that is the TESS team and the community and everybody, will be racing and doing their very best to find these planets in the habitable zone. And it's mostly focused on M-dwarf stars, TESS because of its sensitivity and its period. So, hopefully we'll find, in, I'd say, a dozen or a few dozen, if we're lucky, planets in the habitable zone.
Right. So, and Carl's got up an interior of the cross section of the camera for you, Alexander. So there you go. That's what one of the cameras is made of anyway. And you can see the fisheye lens out front there, or the very curved objective lens at the end that gives part of it gives the wide field of view. So, well, I know that you're being a little bit conservative in what you're saying about what you expect to find, but I think when people look at Kepler, the results from Kepler, I don't think they had that expectation of what they would find when they went out, and so it was. I think it exceeded all expectations from the members of the mission, at least. And I'll bet you anything that TESS will be be full of similar surprises. Will you be looking at anything else besides exoplanets? Will you be trying to look at black holes, for example, or any of that other kind of stuff?
Absolutely. In fact, there's an entire program. It's called GI, General Investigator. And it's run from NASA Goddard, and they actually solicit proposals. And they have a whole list of things people are looking at. Stellar variability, people are looking at all kinds of things there, and the data will be public, so you can look for whatever you want. So it's not black holes per se. If you want to imagine any accretion disks that are very bright at optical, you might be able to see those.
So then that means that it's going to be operated kind of like Hubble is a little bit, isn't it? You're going to have a time allocation committee maybe where people can apply for time on TESS to look at.
Mm-hmm. Except it's less like time allocation than postage stamp allocation.
Yeah.
You're essentially applying for your own postage stamps. Because of course TESS won't point somewhere else. It's only doing what it's planned to do. But you can choose postage stamps, and there's a certain number of slots allocated for that, and that's how it's working. Okay,
all right, and you got to make like Hubble though. You got to make a good science case for what you wanna do. Do you think that the mission's going to last? You said it's going to last. I guess the funding is there for 2 years. Do you anticipate maybe extensions? Are you hoping maybe for extensions?
I mean, like everything hasn't everything been extended nearly as long as possible?
It really has, hasn't it? I mean, as long as it still works, it's hard to just walk away, isn't it? So
especially if he's produced incredible science, right?
Yeah, it could last indefinitely. I mean, it could honestly probably last for decades.
What's the consumable? I mean, do you have like thrusters? I'm not sure.
Yeah, it has. I'm not sure of the exact details.
Okay, because that might be the only consumable you have on board, which is how you point and how you might have to reposition yourself. Maybe Natalia knows. I don't know.
That is something that
to reposition itself, and its orbit is very stable. So
correct.
But like Hubble's constantly having to make sure that its drag is going to make it, deorbit. It doesn't have that problem. So in fact, it does have consumables, but it has no reason to really use them.
All right. So are you using just gyroscopes to point?
I think it uses reaction wheels.
Oh, reaction wheels. Sorry. Yeah. Okay.
So
I see. Yeah. So it potentially could last a very long time. Absolutely. And the orbit is very, very stable for very long. There you go.
Yeah. So Galaxia, we just she was asking, is there an estimate of the amount of newly discovered exoplanets TESS will discover? And you were saying it's in the order of thousands is what's to be expected to come through with TESS. So that's great. So let's see. You've got so we've got the mission. The spacecraft is in Florida. It's getting ready to be loaded up on a Falcon 9 rocket. Are you guys going to the launch?
Most definitely.
Yeah, I am too. I'm going to be there. So we should definitely. So I'm going to put this out there, folks. If you are in town and you want to do a meetup about the Falcon 9, hit me up and I will arrange it. Now I know Galaxy has talked a little bit about coming down to Florida for that launch. So if you guys are serious about it, we will make something happen. I know I'm going to go, and I'm not quite sure where yet. I might just see it from the Causeway, or I might go out and buy tickets into Kennedy Space Center. It just depends on what's available at the time it gets ready to launch. But I'm definitely going. Are you going to go, Alberto?
I don't know. It depends on when it is, actually. It would be kind of cool, actually.
Yeah,
it says, I have to correct. It says no earlier than April 16 on the NASA website. So it's between April and June, I guess. So that's good time to be in Florida, I suppose. Yeah.
Yeah. Does it say no later then? Because it probably says no earlier than.
No early then. Sorry, no early then.
Yeah.
So I guess which I think is June sometime. So I think it's.
Yeah, it's June. Yeah. No earlier than April and no later than June. Yes.
There you go. So spring.
Yeah, spring. That's a good time to, Florida being still not muggy, right, Tony?
Well, it's already starting to get pretty hot by April, but who cares? We'll make do. But I would like to set something up once I know what the date is myself. At least I know I can get my taxes filed before I have to worry about the launch. Not that was an issue, but at least I know that now. And so, excuse me. And so.
So Sarah, actually, I had a question. Can I ask you a quick question?
Yeah,
I just thought about this. So, or either of you. So, I guess when you're doing this, do you have a measure how complete you want to be for detecting exoplanets, of M dwarfs nearby? I mean, or no, you can't know.
Well, right now we're not really worried about that. It's very
okay.
We're not an exhaustive census mission. We're just a discovery mission.
I see. Okay,
well
answered.
Look at the documents really carefully. What we have kind of promised is 50 small planets. Small to even undefined here. So we're just trying to find really the best planets.
I see.
All right. Well, here's a loaded question. I don't know if you guys want to answer it or not, but one plot on Discord is asking: are you happy with the new rollout of the NASA 2019-2030 program as regards to TESS is in the larger vision? So that's kind of political, but I don't know how much you want to get it. So are you happy with where NASA says it's heading?
I'm not sure what that means specifically. Do they want to elaborate at all?
Well, yeah. Why don't you give some more information on one plot? It just says, are you happy with the new rollout of the NASA 2019-2030 program?
Because they released the budget, basically.
Yeah,
right?
it's the new budget with the cutout of the ISS and killing W first and stuff like that.
I mean, I think rather than get into personal and negativity here, we believe that TESS is not related to that budget. So TESS is a go. It's going to
right.
Exactly.
And it's important to realize that this budget has to be approved, and this is just a recommendation, and it's still way early in the process now. So there's no.
I have a quick question about the process when it comes to the launch and designing a mission. Kind of just in general, how are launch systems selected, things like that, in the overall process for a mission like TESS? Because I got to talk to Dr. O'Meara at one point about LUVOIR and the process of how to get those things approved, and it was absolutely fascinating. So I was wondering if you could elaborate on that just a little bit.
Well, TESS is not too big. It's kind of like it's about, I don't know, I want to say 5'5" tall. It's like two giant washing machines on top of each other. It's not that massive. So in the case of TESS, it's most likely like the lowest bidder, if you will. Kind of go with an option that's a good price. LUVOIR is a whole different ballgame. It's so giant. Like there's no launch vehicle that is flying right now that can support it. So it's a totally different story there.
One thing I want to clarify about TESS is that it's going to be looking for planets, or it's going to be looking for dips in brightness around stars inside of our galaxy, correct? It's not going to be looking at it's not going to be able to see this dip in brightness from another galaxy, is it?
That's right.
Yeah, and the reason I bring that up is there was recently a story about exoplanets found in another galaxy, and that was done by using a lensed quasar light that happened to look a little bit funny after it was lensed by a foreground galaxy. But the conclusions reached from that were a little bit, they said, well, it could be planets, but it could also be a lot of other things. This TESS will be looking at things within our galaxy. And
remember the animation we showed earlier? Very close to home, as close as possible.
That's right. When we saw the zoom out thing, and the another important point about this kind of science, folks, is that we need time series data. We need to do this over a period of time in order to see the results and brightness.
It's a nice pose for him, though.
Yeah, he's like, mind blown. I have a quick question from Andrew Planet while we wait for him to reconnect. Is TESS serviceable?
No.
Not right now.
No. And then from Philip W., hypothetical question for the panel. Could TESS detect a star in orbit around a black hole using the transit method?
No.
No. And could kind of elaborate maybe a little bit. Why is that? What obstacles? What are the difference between an exoplanet and transiting in front of a star and a star transiting in front of a black hole or high energy object like a neutron star?
Well, those objects are very faint. They're so basically black, will have no visible light unless there's light falling on it from bodies that are being absorbed. So there's nothing really to block out. The other thing that we should point out, a negative on TESS is our pixels are so giant that objects that are very far away, like, we'll just not be able to sort through them. You know, our pixels are quite big on the sky. And so we can't have that, we don't have a lot of like fidelity to see little tiny things in the background, unfortunately. So we're really thinking of bright foreground stars, not very distant, more specialized things. But the neutron stars would be not visible to TESS. They're way too faint. So we couldn't do that at all.
I would think the only way you would be able to do it, would be in X-rays, would be if you have a quasar and you have those jets and then the object passes in front of the jet, you could maybe do it. But TESS can't see in the X-ray. So
the TESS cameras are like that big.
Yeah.
Yeah, that's right. So
like galactic astronomy. It's not that. It's like the bright stars. And it's just specially designed just for that problem, actually.
So could you talk a little bit about that as well, like the types of...
just one more thing, because it was...
Sure.
There's one little interesting thing that people like to think about, but if an object, you know, let me think for a second. Actually, never mind.
And now the secrets go forward. Tony, can you hear us?
Oh,
can we hear you?
I can hear you the whole time.
Awesome.
It's
okay, good.
And this whole thing is being streamed still. It's just my particular upload internet. Sometimes it gets messed up, so everything is still being streamed okay. So there were. I'm going to go ahead and ask this question, but I don't know if it's part of your candidate question or candidate stars. But is Dryad Dash is wanting to know if you've got any plans to look at the TRAPPIST-1 system with TESS.
Well,
is it one of your candidates?
TRAPPIST-1 is one of our candidates. Anything that's of interest, like TRAPPIST-1, will go on our special list for our special postage stamps. However, TRAPPIST is really faint, actually, even though it's like super exciting and in the news. It was discovered with, I think it was either a 0.5 meter or 1 meter telescope. And remember, TESS is really small. So any star like TRAPPIST-1 or that's of interest, it gets on our list of things, but it's not going to be something. TRAPPIST-1 itself, TESS could probably barely see could see the transits, but not very well. So yes, anything interesting will be on the list, but it's not really bright enough to be one of the prime things we're interested in.
All right.
Okay. And excuse me, can you remind us what kind of information you can get out about an exoplanet from a transit? When a planet moves in between the Earth and its star, you get a dip in brightness. What kinds of things can you learn about the planet from that information? Natalia, maybe?
So some of the parameters, so you fit a curve to that, and that will give you information about, you can estimate the planet radius, and a little bit about like the effective temperature of the planet. But you do have to end up doing spectroscopy and follow-up measurements to better understand things like the mass of the planet.
Right. And that would be something called the radial velocity method, which looks at the wobble of a spectrum as the planet pulls the star from one side to another, causing the spectrum to move back and forth. And from that, you get some idea of the mass of the planet. So, good.
Yeah,
okay.
That's a good time to add that TESS at the beginning. It's literally the tip of the iceberg.
Right.
And there's like a giant team of people signed up with telescopes all around the world to do those things Natalia was mentioning. So just see that dip, estimate the, like she said, but there's way more to do, and people will be doing all of that.
Yep. Okay. Well, all right. I guess I think we got to all the questions. Did I miss anything, Carl? Do you see?
I don't think you did, but I do have one quick question.
All right.
We've been talking about the different objects that TESS could or could not observe. Could you kind of really briefly go through the stars that it will be looking at, what class they are, and why that's kind of important? I know you said photons are currency, so I'm assuming it's something along those lines.
I think nominally it's F through M type stars is like the range on like the HR diagram, if you're familiar with that.
Okay.
And our sun, Sol, is a...
I think it's a G type star. Yeah.
Yeah, okay. So, all right. Well, that answers that question. Thank you.
Okay, well, while we're on the topic of mission updates, Alberto, you want to give us, we got a couple minutes. Give us a little update on JWST. I know it made it to California, didn't it?
It's made it to California. We are working constantly on the sun shield. We just completed our second folding of the sun shield, and we're going to install the thrusters on the bus next week. The OTE, which is Otis, which is the telescope with the instruments, is still in airlock waiting to enter the clean room, which we'll enter in the next couple of weeks or so. And then we're going to have to do a lot of acoustics, vibrational, thermal, vacuum tests for both the sun shield and the spacecraft. And after that, sometime in late summer, maybe August, September, we will mate the telescope to the mirror itself with the instruments to the sun shield and the bus. And for 25, 30 days or something, everything will be deployed in almost the flight configuration, which will be interesting to see. So you should come, Tony, and check it out.
I would love to. So is that an invite? Are you inviting me?
Come. There you go. Sure.
Yeah, sure.
Lots of us will be there, you know. So everything is going to plan. Lots of work. We're working diligently on everything else. So
cool. All right. Well, thanks, Alberto. Okay, guys. Sure. Well, TESS is coming up. A couple of months. It's in Florida right now. The testing has been complete. It's just getting ready to be loaded onto the rocket for the launch sometime after the middle of April, and hopefully before summer. And I will keep you posted on any of the launch dates as they become available, and we will make arrangements to maybe get together to maybe see it in live person. This might be a first chance for space fans to get together and see this thing. And I want to just take a minute. I want to thank Dr. Sara Seager and Natalia Guerrero for taking time out to talk to us about TESS. Exoplanets are awesome. You guys know that. This is the next era of space telescopes looking at exoplanets. So we've got exciting times ahead of us. Golden age of astronomy, folks. Golden age of astronomy. I'm just keep saying that. Next week, we're going to be talking with, we got our telescope talk hangout on Wednesday, and I believe we have an Astro Coffee hangout with Carol Christian coming up next Thursday. So I'm working on getting those done. Thank you guys very much for joining us today. I wish you nothing but a success in the launch. Here's keeping our fingers crossed that the Falcon 9 doesn't have any kind of problems at all. Real quick, is it going to be a reusable rocket, or is it going to be one that's brand new? Do you guys know?
It's not reusable.
So it's a brand new rocket they're using, one that hasn't been used before?
Exactly right.
Do you have to pay extra for that, or do you know?
I don't know.
All right. I was just wondering. So everything's like, $90 million? Yeah, okay. I think I can maybe get a launch going too. So, okay. Well, anyway, thank you guys so much for joining us. And I want to thank you guys for watching. Please like this video. Please share it. Please support Deep Astronomy by letting people know about this Hangout series. And I will see you guys next week. And as always, keep looking up.